celebrate our co-fellows, but also give them an opportunity to showcase some of the great research that they've done last year. And so we have 4 fellows. 3 of them are here and will be presenting, and the 4th has defended his thesis last week and is taking some time off, but he was kind enough to record his presentation, and so we will be showing a video of his presentation. And so without any further ado, we're going to start with the first fellow and presenter, who's Thomas Bougher, who works with Professor Bougher right there, and he's going to tell us about some of the work. So please join me in welcoming Thomas.
As you said, my name is Thomas Bougher. I work with Bougher. I'm from the School of Mechanical Engineering, and I work primarily in nanoscale heat transfer. So I know heat transfer is everything. That's something that everyone at COPE is really excited about. I'm sure you're really excited about this talk. First, I'd like to acknowledge my collaborators and my funding, especially within our group. Rendra Singh, he has been really important in helping us make materials, do a lot of electro depositions, and also other collaborators. Jeff Hernandez from Dr. Brown's group has been helping me recently make some thin films as well. We also have some outside collaborators that help, and funding from COPE, as well as the IGER program. So first I just want to go over kind of one of the application motivations for the heat transfer materials we make. This is a thermal interface material, which is typically used to combine 2 materials, a hot and a cold material, to dissipate heat. A common application would be a flip chip assembly like we have here, and you have a processor, you have a heat sink. You want to join these 2 materials, but on the macro scale, even though they're smooth, on the micro scale, there's probably only 1% contact area. And so it's a lot of surface roughness. You have a large temperature drop at the interface, which rises your device temperature here and prohibits heat dissipation. So what happens is, if you introduce a thermal interface material in between the 2, you can actually decrease that temperature drop, and you'll reduce the peak temperature of your device, which can increase your electronics longevity and reliability. And another application a lot of people are interested in terms of thermal transport and polymers is thermoelectrics. Different goals there, really focusing on Seebeck coefficient and electrical conductivity rather than thermal conductivity. So we're really focused on high thermal conductivity as opposed to thermoelectrics, which want to keep that thermal conductivity low while increasing the electrical. So mostly in this talk I want to talk about more fundamental aspects of thermal transport, but first I want to go over some of the applied work that I've done in the past. So we created wide area arrays of polythiophene nanofibers. We electrodeposit these in a template, and we can use these as heat transfer materials. We've shown that over a wide array of heights, we can actually increase the thermal conductivity compared to bulk polythiophene by about a factor of 5. If you include the void space in the array, it's actually a factor of 10 increase compared to the bulk polythiophene material. We've also demonstrated these devices on real applications, like real applications. This is a simulated RF device. We actually can grow directly on this heat spreader, grow our material so that there's no contact resistance and there's good adhesion. We've cycled this device up to 200 degrees Celsius, and it's stable, showing excellent thermal stability, which is good for a lot of high temperature applications. And finally, we found that our material is actually is competitive with commercial materials. This is just a range of different commercial materials that are available. And a lot of the ones for high temperature here, we actually can have lower thermal resistance. So now other people in our group are actually working on scaling this process for commercial viability. So polymers are traditionally considered thermal insulators. They have a thermal conductivity of about 0.1 due to the disorder and the weak bonding between different chains. But some recent groups have shown that when you stretch and align polymers in a certain way, you can actually achieve very high thermal conductivity because the polymer backbones have very strong bonding and they can transmit lattice vibrations very effectively. So David Cahill's group at UIUC showed that for a commercially available drawn microfiber, you can get 10 to 20 watts per meter Kelvin, which is actually consistent with a lot of steel alloys. So that's a significant increase in conductivity. And then Gong Chen's group at MIT showed that with a draw ratio of 400, you can actually get 100 watts per meter Kelvin in nanofiber. This is the thermal conductivity of pure metal, which is really kind of a shift in the thinking about polymers, where you can use them as good heat conductors, not just insulate. The one thing also about this is all the previous work has really dealt with insulating polymers in terms of the non-conjugated systems. So no one really understands how this mechanical drawing would affect the electrical transport of the systems. This is my experimental setup, but it's also kind of a result slide, because a lot of the work I've done in the last year is setting up this pump probe system. So this is called time domain thermal reflectance. There are quite a few of them around now, but it's a very accurate way to measure thermal conductivity of thin films and interface conductance. So what we do is we take a Ti-sapphire femtosecond laser and we split each pulse into a heating pulse and a probe pulse to sense temperature. We modulate the probe pulse so that we can use a lock-in amplifier to extract our signal. And then we use a mechanical delay stage to vary the time in which the probe pulse hits the sample surface after the heating pulse. And this way we can plot out a temperature decay curve over about 7 nanoseconds. And with this short time delay, we can actually fit this temperature decay to a heat transfer model. We can extract thermal properties of multi-layer thin films. It's nice because it has a high spatial resolution. You can look at really thin films. And we also have an optical cryostat, so we can go from 5 to 500 Kelvin, so we can look at some of the more fundamental aspects of thermal transport. We're also getting a electrical probe stage in the optical cryostat, so we can do simultaneous measurements of electrical and thermal. And this is just what our device stack looks like. You need to deposit a thin metal film on top. That serves as the transducer, which the reflectivity changes of the metal with temperature, and that's how we measure the temperature. And then we have some sort of thin film, and then a substrate behind it, glass, silicon, really whatever, as a substrate.
So sorry, can you go back? So
Yes.
what's reflecting about? What's the change in reflectivity?
So the certain metals at different wavelengths have a thermal reflectance coefficient. So the reflectivity of aluminum at 800 nanometers changes significantly with temperature. So so this is, we're absorbing basically just at the surface here the heating pulse, and then the high reflection of the 800 nanometer of the surface, it imparts the modulated temperature signal back into it. So this is just a plot of thermal and electrical, it's electrical resistivity and thermal conductivity. Unfortunately, they didn't plot electrical conductance here. So the highest conductance of both would be up in this corner rather than over here. But what this shows is electrical resistivity spans more than 20 orders of magnitude. So there's a wide variation in the electrical properties of certain materials. Whereas thermal conductivity, you only have about 5 to 5.5 orders of magnitude. So when you're talking about manipulating the thermal properties of a material, a factor of 10 is actually a significant change, whereas you might not think anything of that by just changing the electrical conductivity of the material, a factor of 10. So as I talked about some recent work, people have taken polyethylene nanofibers up here to metal-like thermal conductivity, and then polyethylene films up to another high thermal conductivity, but these are obviously highly electrically resistive. We've taken polythiophene nanofibers up into this range here, improving the thermal conductivity, but not really looking at the electrical properties. And we're looking at actually enhancing or doping these polythiophene and other nanofibers, and then also looking at doped polymer films and seeing if we can enhance the thermal properties of those. So our collaborators at UT Austin have done single fiber measurements as a function of diameter based on the polythiophene nanofibers that we created. And what this shows is that there's a sharp increase in thermal conductivity as the fiber diameter decreases. And through using certain techniques I'll talk about in a minute. But first I'm going to show that another group showed that P3HT actually has the opposite trend. So they show a decrease in thermal conductivity as the diameter decreases.
Just to make it clear here, the polythiophene nanofibers you're talking about, were these electrochemically prepared?
Yes, these are electrodeposited in an AAO template.
So then, did you reduce them, or are those the oxidized form that you're measuring?
Reduced.
How did you reduce them?
Through we de-doped them through the KOH, I believe. render that.
Yeah, it's reduced like through the chemical processing, like after electropolymerization when you wash them with KOH, so most of the dopant is out. So we actually measure the electrical conductivity, they are like insulated.
Okay, very good. But so there's a different trend with P3H2. So we used when we looked at our fibers with X-ray diffraction, and we saw no crystalline pattern, so they looked completely amorphous. Then we used polarized infrared absorption, and we noticed that there is a degree of chain alignment in the tube axis. So we hypothesized that while there's some general order in the tube direction, there's no actual crystallinity or long-range order. In the P3HT fibers, they showed that, or they used wide-angle X-ray scattering to hypothesize that the crystals in this case were actually orienting themselves so the chains were perpendicular to the nanotube axis. So this is why they're seeing a reduction in thermal conductivity while we see an increase. So you can, depending on your polymer system and your processing technique, you can see different properties based on nanostructures. We also looked at the temperature-dependent thermal conductivity of these nanofibers, and we see a T to the N behavior for different diameter wires here. T to the 0.4, T to the 0.2, just a weak temperature dependence, which is consistent with amorphous materials, with just a gradual increase in thermal conductivity or plateauing around room temperature, which is consistent with a disordered material. This is comparison to the crystalline fibers that Cahill measures, where they have a 1/T dependence, which shows that anharmonicity is present in these fibers based on phonon-phonon scattering around room temperature. So in my most recent work, I've been looking at polymer thin films and TDTR. And first we just started with some P3HT. Jeff Hernandez has been making some spin-coated films for me. And we want to just look at this because this is kind of one of the most common systems measured for thermal conductivity. Although there aren't that many temperature-dependent measurements of thermal conductivity. So our measurements are here. We show at room temperature there's really kind of a plateau in thermal conductivity. Even though P3HT is crystalline on a long-range scale, there's really not a high degree of crystallinity. It's more on the nano scale. So we would expect this kind of behavior where there's not much of a thermal conductivity increase. And then you have sometimes the thermal conductivity can be slightly higher. This is a highly doped film, although the electrical conductivity is still so small that we don't think that's not really what's contributing to that change in film. Then we also looked at some P.PSS. This is some high conductivity grade P.PSS from Sigma Aldrich. And we measured the conductivity about 60 Siemens per centimeter. And what we see here is we actually see a strong temperature dependence around room temperature, which is, it doesn't fit the T to the N behavior that you would expect from maybe this sort of polymer film around room temperature. There's a much stronger increase in thermal conductivity in this system. So, and this only other temperature dependent measurement, P.PSS, is much flatter, not really showing the same dramatic temperature dependence, although they also didn't go to lower temperatures. So it's hard to say whether their behavior is the same or different because they really measured a very, very narrow temperature range. So it's likely that there is some other contribution to this change in thermal conductivity besides what you normally see in an amorphous polymer system. But we really have to investigate this more to really understand what it is. In terms of the electronic contribution to thermal conductivity, there is a theoretical contribution that's typically in metals called the Wiedemann-Franz law. The electrical contribution to thermal conductivity is proportional to the electrical conductivity. And this is really true in systems with free electron systems. So it may probably not apparent in polymer systems, but there could be some contribution to the electrical to thermal conductivity. We're not really sure about that. There really isn't any published data on this yet. And I'm aware of two unpublished studies. One shows a strong dependence of electrical and thermal conductivity, and one that shows very weak dependence. So it's something that's really an unanswered question right now in the literature that we're interested in finding more about. The other one interesting thing about this is these two plots contain about 50% of all temperature-dependent thermal conductivity measurements for conjugated polymers. So really there's not much data out there. So in conclusion, we've shown that nanoporous templates can lead to high thermal conductivity, and we can use this high thermal conductivity in real heat transfer materials. we also find that these are completely amorphous, which has some different transport properties, which we'd like to see how that affects the electrical conductivity. And we also find no previous reports of electrical and thermal conductivity, the relation between them in conjugated polymers. And also, there really are no measurements of thermal conductivity for highly electrically conductive polymer. So my future work, I'd really like to focus on measuring thermal electrical conductivity over a wide temperature range and see if there is any relationship over several different polymer systems. And then also see how the electrical conductivity is affected in the nanofiber system. And then finally, possibly looking at some mechanical stretching to see if we can align chains to enhance both types of transport. And with that, I'd like to thank you and take any questions.
Thank you. We have a few minutes for discussion, questions. Let me start. I was wondering on what time scale do you measure the changes of the temperature? You have that control.
So we typically measure about 100 picoseconds out to about 7,000 picoseconds or 7 nanoseconds. So about 0 to 7 nanoseconds. So it's a relatively short time scale, but it's still an area where diffusive transport still dominates. So really not looking at equidistant transport.
Because the amount of light that actually goes into the metal for the heating depends on the structure of the dielectric metal, so the thickness of the polymer layer and the refractive index of the material itself is that influence. So you take that into account.
Well, so I don't think, no, we don't. The idea is that yes, it will change, but I'm not sure that will actually affect. If we're just using the pump pulse to heat, and the reflectivity is over a very small range. We're only changing the temperature of like 5 or 10 degrees Kelvin. So within that one system, the reflectivity might be different, but we're not making an absolute measurement. This is just a relative measurement of the change in temperature.
So you're outside the regime where you have relaxation or thermalization.
Oh yeah. So the thermalization happens typically between about 1 to 100 picoseconds. So we don't start measuring until after the electrons have fully transferred the heat to the lattice.
The other questions? John?
In a polymer sense, the work that you put up there on the cis-PDO is interesting because of the high degree of orientation you get in those fibers. Yeah. I assume that's polythiophene, right? And so it makes me wonder if people in general look at hydrogen bonded fiber materials, nylons to Kevlar, for example, these kinds of applications.
So this actually is actually a Kevlar right here. So this is the only study that's looked at that.
Which one?
Well, actually, so
that was polyethylene.
So I guess this is polyethylene. They also did Kevlar, but I guess I didn't put it on this plot. But they looked at it. It does have a similar trend in temperature dependence. They looked at about 5 or 6 different commercially available drawn fibers, nylon fibers, I think, and they found pretty much all of them, because they were so stretched, showed a high degree of crystallinity and high conductivity like this. So yeah, that's the problem with that is there's no real way to use that in a material right now, because you just have a fiber. You'd have to somehow align a group of them vertically between the material or something like that. So people are working now to create mats of drawn fibers so that they can laterally spread heat, but it's still kind of in the early days.
I think you might look into various membranes and hollow fiber membranes as technology that you might be able to use.
Okay, I guess we have to move over the program, so let's thank